Happy Friday, everybody. My pleasure to welcome you to the next episode of YFTT, the Yugabyte Friday Tech Talk series from engineers for engineers. Today I have with me Tanuj Nayak. He's an engineer on the query layer and the languages part of the database team with an interesting topic. So Tanuj, would be great if you could start with a quick introduction about yourself, and then let's dive into the topic.
Yeah, hello everybody. Thanks Kannan for the introduction. Well, I'm Tanuj, part of the LRT team. And over there we work on query execution, optimization, and that part of YugabyteDB on our team. I've been here for 1 year, before which I was at Carnegie Mellon at the database research group. But today, on this beautiful Friday, we're going to be talking about table partitioning in YSQL and how we can smartly use the ybhashcode feature to smartly interact with said table partitions. Okay, so speaking of table partitions, let's think about what table partitioning actually is in the world of YSQL. So the default way that tablets are configured across clusters is that we have tables that are split into tablets, and these tablets are essentially chunks of rows that are spread out through a cluster. Now the question is, how do we decide?
Did you want to share your slides, or you're going to do that a little later?
Oh, I'm sorry, I didn't realize I wasn't sharing. Oh my God.
No worries.
Oops. Okay. So yeah. Okay. So again, let's start from the.
No, I think it's good. I think, yeah, your intro was good. We can now go into the topic. Yeah.
Yeah. Sorry about that, guys. Didn't realize I wasn't sharing. But anyways, so again, starting off from where I left off, again, I was talking about how we are going to be talking about table partitioning in YSQL, wherein we have tables that are split into various tablets that we can throw all across the globe, all across your clusters. And now the question that we'll be diving into this talk is how rows are, divided into these various tablets. How do we decide which row from a table goes to which tablet? So over here, to the untrained eye, you might be like, okay, so clearly the orange rows go to the orange tablet, blue rows go to a blue tablet, blah, blah, blah. But let's dive into further detail there and see what makes a particular row go to what tablet. And the default way this happens right now in YSQL is we assign a particular value to each row. And these values here are called hash values. And these hash values are essentially integers that run from 0 to 64K. And they essentially tell you where a particular row will be designated in your space of tablets. So for example, this orange row here might have a hash value let's just say 500. And now, as this diagram suggests here, every tablet here consists of a range of hash values. So the first tablet has hash values from 0 to 512. Hence, any row whose hash value is 500, in example, will go to tablet 1, and so on and so forth. Let's go into further detail on that and take a more concrete example. So for example, if we had a table with 3 different columns, and 2 of the columns can be designated, or any subset of the columns can be designated as what we call hash columns by the creator of this table. In this particular example, we choose the first 2 columns to be designated as our hash columns. And the important part about these hash columns is that these hash columns are used to determine what is called the hash value of this row. And the way we do that for a row is we take the values inside hash columns and feed that into a special function that spits out the hash value for that row. In this particular example, the hash code here is 1026. And the inner workings of that hash function, how we spat out 1026, are not important for now. But essentially that tells us via our mechanism from earlier that this row, whose value is 1026, should go in tablet 3 by our demarcations here. And that brings us to what we know as ybhashcode. So ybhashcode is a function that is a wrapper over this beautiful hash function here. So essentially, we expose this hash function to the user via this ybhashcode feature. So again, this is a function, much like your everyday Postgres functions, such as max, min, average, standard deviation, those types of things. This is just another built-in function you can use in YSQL. Now, again, just to reiterate, the beautiful part about ybhashcode is that now you have access to this hash function, and hence you can make queries in YSQL based off of hash-based location, or one might say physical storage order. So since you have a weird access power to the actual physical location or the hash-based location, you can take advantage of spatial locality. So now if a user wanted to query a contiguous slice of the tablet, let's just say of a table, let's just say they wanted all the rows in tablet 2, they could query all rows whose hash values range between 512 and 1024, and enter that into their YSQL shell. So such queries are not restricted to just one tablet. It's just you can do any query on your hash codes. For example, over here, you can ask for the contiguous slice of hash codes between 400 and 700. And while this spans between tablet 1 and tablet 2, you still are looking for a contiguous chunk of your table right here. And then any benefit that comes with spatial locality, this whole contiguous selection feature using the ybhashcode allows you to do that. So let's dive further.
I guess one way to think about it is it helps you go after a slice of data in your very large table that is co-located in the system, right? It's a way of slicing your very large table into portions that are physically near each other.
Right, yeah. And before this ybhashcode feature, there was no way to specify that, hey, I want a contiguous slice of data. I don't want to spread out multiple queries throughout multiple tablets and multiple parts of the world. Yeah, so let's dive further into ybhashcode usage. So again, it has the same syntax as any YSQL function. It is a function that takes in parameters, and these parameters can really be anything that fits in a primary key. They can be column references, they can be hard-coded values of multiple types, and the usages function can go in your select target or your select filter. So speaking of uses of this particular function, you can do a few things. So given that now you can specifically point at tablets and specific places in the tablet saying, hey, I want this row, or I want to check up on this row, it is very easy for you or a support engineer to check the health of any particular tablet, or check the health of any row whose hash value might be 24 or something like that. So it's nice for debugging purposes and just sanity check purposes. Another nice use case is it allows you to randomly sample rows, since you can point anywhere on the table in the hash space. And this allows you to do nice statistical things, such as estimating table sizes, estimating averages from a sample chunk of your table data, and really a lot of statistical aggregates from there you can estimate. Last but not least, you can launch distributed parallel queries now with this. So since you can launch multiple different threads that operate on distinct non-overlapping hash segments, in other words, they can operate on non-overlapping segments of your table, you can do a lot of just Spark style parallel jobs and on your tables right now because of this. So let me quickly go into, yeah.
So Tanuj, there are some questions. So the first one is, are the hash code boundaries for each tablet known?
Hashcode boundaries for each tablet known. So in our CQL offering, there are neat functions to tell you what the hashcode boundaries are. But for right now, you need to go to platform and determine your hashcode boundaries from there. But we're looking to make determining hashcode boundaries for tablets much easier on the YSQL side as well.
So maybe I can add some color there. So yes, of course, the system internally knows what the hash code boundaries for various tablets are. And today we expose that data through more admin APIs, like through the YBadmin tool. So there are more like internal APIs that you can use to build, as well as through these administrative tools. Today, that detail is not exposed through the Postgres or the SQL interface itself. However, the point that Tanuj made in the previous slide is important, where it's actually not that important for you to think in terms of tablets. What you want to think in terms of, you have a large table, and how do I slice it? There is a 0 to 64K hash space. I want to break it into meaningful slices that are co-located on physical storage. So in the common case, you wouldn't worry too much about the tablets, because let's say you took a slice like 0 to 512. Maybe it lands on one tablet, maybe it lands on two tablets or three. But the good part is you're going after that small subset of data across your whole table. If you think it's landing on too many tablets, you can make it smaller, like 0 to 256. It's more a matter of deciding how many subtasks you want to break up your 0 to 64K space into when you're, say, writing a parallel query job, or you're trying to sample some portion of data.
Yeah, thanks, Kannan.
There's another question, Tanuj. Is there a way to find this data skew across tablets?
Of course, yeah. So right now, you can launch your regular select count stars over any particular table and over any particular filter. So over here, if you say that, if you ask for a count star over all hash values from 0 to 512, right? And then next compare that with a count star over all hash values from 512 to 1024. And then you can compare how much data or how many rows are stored in each of these hash buckets. And if that comparison tells you that these row counts are not uniform, then you can learn about data skew on your table.
Exactly, and I think the demo will also make that clear. Yeah.
Mm-hmm. Yeah. My demo kind of will touch on that as well. Yeah. Speaking of which, if there are no more questions, I think we can move on to our little demo right here. And okay. Oops. Yeah. So what I'm going to do, I'm going to pull up a terminal wherein I have loaded 10 million rows into this table called sample. So right now I've turned timing on, and since it's 10 million rows, and I'm really just running a cluster locally on my laptop, so not that much horsepower to work off of, it takes 13 whole seconds to do your global count star on sample. Now, however, that's in order to get an exact count. That's what's going to happen. But what you can do is you can get a sample segment of our table, see how many rows are there, and then extrapolate from there. So for example, if we did a query like this, where we are getting a count star in all rows whose hash values are less than 1024, and extrapolating that number up to the whole 64K hash space, we can get a good estimate in what appears to be like much less time, like 1.3 seconds, 1.4 seconds right here. And if you amp up this, if you amp up your sample size and adjust your extrapolation accordingly, the amount of time you take to do this will increase proportionally, but your estimate will also get more accurate. So
here, of course, we are assuming that the hash distribution is good, right?
Mm-hmm.
And this is maybe confirming that the hash distribution is in fact good. And these are all other signals. If instead you found that this was not coming up to your original 10 million number, then maybe the first 0 to 2K portion had more data or less data than average across the entire table. So those would be the signals.
Right, exactly. This is a neat way to measure data skew, right? If our initial sample had way more hash values or way more rows than the average, then this would be a giant overestimate right here. So yeah, this is a neat way to measure data skew. We have another question here. Is there any query which I can run to check all tablets have uniform data for specific user table?
Yeah, again, not through the SQL interface specifically, right? You would have to get the tablet boundaries first, like we talked about in the admin command, and then use this technique here through SQL, and then confirm what the number of rows is in each one.
Yeah.
Of course, there are other proxies, like you can look at disk size across the tablets through the admin APIs. That will also tell you whether some tablets just have much more data. Yeah, we can keep going.
Yeah, does it answer your question, Jamin? I'll take that as a yes. But okay, so this is just one application where you can take an aggregate such as count star, do it on a sample, and upscale that to the rest of your table to make an accurate sample. But what if you wanted an exact value? What if you want an exact value for our row count? So what you can do, so take this observation here that if we do a count star on all rows whose hash values are less than 1024, it only takes 1 second or 1.4 seconds as opposed to the 13 seconds to do the full count star. So that begs a question that what if we divided our whole hash space into 1024 sized hash chunks, right? And we took all these hash chunks, counted the number of rows in each of these hash chunks, and added them up in parallel. So theoretically, if we had infinite processors, you could, or like infinite parallel resources, you could do the entire count star in 1.4 seconds. This is kind of reminiscent of the whole map reduce protocol from our beloved map reducers such as Spark and whatnot. So right now we have CQL integration with Spark in a similar way. And we are working to integrate Spark with YSQL as well to display such parallelism and take advantage of this new ybhashcode partitioning feature. So to get accurate reductions like this. Yeah, so I think that would be my demonstration of what you can do with ybhashcode. Again, like it's in its infancy. The next target from here would be to get other applications to use this feature and really take advantage of this. And really looking forward to that. Thanks a lot for sticking around, everybody, despite the small delay. I really appreciate it. If you want to join us on Slack and learn more, feel free to do so. Star us on GitHub, of course.
Maybe I would, there was one question whether we support range partitioning also, and later, it was answered to saying, yeah, we do. But I think it's worth adding that context, Tanuj, maybe you could give a feel for how come my vanilla Postgres or MySQL didn't need such a built-in function. Why is it that Yugabyte needs this ybhashcode function? Right? So
yeah. So I can chip in with my 2 cents right here. So the databases that you just described are single node databases, and our whole stake is that we are a distributed database. Since we're a distributed database, we're going to have data disaggregate all across the world, right? So over there, we have much higher need for directives that say that really control where our queries are going in the world, or how spread out our queries are. So for example, in Postgres, let's just say you can't exactly control where in the disk you are getting rows from. You aren't hitting as big of a penalty as getting rows from Netherlands and also from LA at the same time. When you could really when you really don't care where the rows are coming from, you just need 5 different rows.
And, and that is one aspect for sure, the fact that it is distributed. A second is that in traditional databases, the primary key or the index is organized by a sort order, typically like ascending or descending. So suppose you have a text column is your primary key. The way you might slice your data, if it's ordered in a sorted manner, you might say, give me the slice from A to C, C to E, and E to J, and so on, right? Whereas in Yugabyte, we give you the choice of both hash distribution and range distribution. And for hash distribution, the user now needs a way to express their intent that they want to go after, this slice versus that slice. So that also triggered a need to introduce this kind of a function. And if you think about like the history of other distributed databases like say Cassandra, it has had a similar concept. I mean, there it's called the token function or the partition hash function. And connectors like Presto and Spark, the parallel, I shouldn't say connectors, but I should say the parallel query engines like Spark and Presto have used those Cassandra token functions or the partition hash function as a way for working on slices of the data and writing parallel query frameworks. So we are hoping to do that same thing on the SQL API as well, working with projects like Spark and Presto to be able to write parallel query computations in a more locality and slice-aware manner on top of data that's sitting in Yugabyte YSQL tables.
Yep. Yeah. Thanks, Kannan. There's another question. Is the data inside a table also ordered by the ybhashcode value? So if your primary key on your table is hash partitioned, so in other words, your table itself is hash partitioned, this is absolutely true. So all the rows here will be ordered by hashcode. That's not the case, however, if you didn't specify a hash primary key, and you will have your table being range partitioned.
So in fact, it'll be interesting in your demo to just show a select. Initially, let's just select the column with like limit 10, and then also do select ybhashcode with limit 10.
Yeah. Absolutely, yeah. That's okay. So let's just do a quick select everything from sample limit 10. Oops, sorry. What happened here? Okay, sorry. Made a typo there. Okay, select everything from there at limit 10, right? We get these values, seemingly random order. However, if we also spit out the ybhashcode as a third column, here's what happens, right? So you're ordered by hashcode right here. So let me amp up the limit. And then, yeah, as you can see, it's naturally ordered by ybhashcode right here. Okay, yeah, so we have another question right here. In case of parent-child tables, can I designate the parent key for hash object and have the children store close to the parent? Okay, so that is a collocation question. It is ordered by, yeah. So does it answer your question, Pete? Mingui's answer?
Yeah, I think so. Yep, thanks.
I think the more common thing is usually like a primary key where one portion of it is used as hash and then subsequent portion of it are used as ascending or descending. That's very common in like IoT like data or even like order details table, where the order ID might be a great candidate for being the hash portion of the primary key to distribute. But then for a particular order, all the line items within that order you want to store near each other. So you might say order ID, comma line item, and use hash for the first portion and line item for the ascending portion. We do have a hard stop, but if there are more questions, join us on the Slack channel, YB users, and feel free to continue the discussion there. Thank you, everybody. Thanks a lot, Tanuj.
Thank you, Kannan. Thank you, everybody.